Welcome learners. This is Dr. T. Gangaram, lecturer in statistics, SVA Government College, Srikalahasti. The objective of this video lecture is to derive the memoryless property of exponential distribution and two examples of application of exponential distribution. Actually, what does memoryless actually mean? Imagine you are waiting for a bus. Usually, the longer you wait, the newer the bus becomes. But the exponential distribution does not care about the past. The battery analogy is if a light bulb is memoryless, it means that a bulb that has already lasted 100 hours is just as likely to last another 100 hours as a brand new bulb is to last its first 10 hours. They are both equal. The probability of failing in the next interval depends only the length of that interval. It does not depend on how long the component has already been in service. Let us look at the bus stand paradox. Waiting for 15 minutes versus waiting for 45 minutes versus 15 minutes. Here the scenario is, suppose at a bus stop, the bus arrives randomly with an average wait time of 1 hour. That is 1 by lambda is equal to 60 minutes. 1 by lambda is the average of exponential variate. You arrive at the bus stop and start your stopwatch. Wait time elapsed. That is A. 45 minutes have passed, no bus arrived. The remaining time is you hope to wait only for 15 minutes. The memoryless reality is in an exponential distribution, the probability that you wait 15 more minutes after 45 minutes is exactly same as the probability that a person who just arrived waits 15 minutes. These both are equal. Your 45 minutes has no weightage. It lost its memory. It is very efficient for learning. That shows that the probability that x greater than 45 plus 15, given that you have already waited 45 minutes, is equal to the remaining 15 minutes only. Probability x greater than 15. The wasted 45 minutes do not give you any credit towards the next arrival. It does not influence the next arrival of the bus. The system has no memory of your 15 minutes wait. Let us look at the light bulb example in detail. Do components age? Given a component's life x follows an exponential distribution with a mean of 1000 hours. The fact is a component has already functioned 900 hours. Here our A is 900. The mathematical surprise is the probability that it lasts for at least 100 more hours is probability of x greater than 900 plus 100, given that x greater than 900 is equal to probability of x greater than 100. The learning point for students here is the exponential distribution assumed no wear and tear. Every moment is a fresh start for the component. This is used to model things like radioactive decay or the time between phone calls. The role of randomness, the fixed events. If a bus is scheduled for 10 a.m., 11 a.m., 12 a.m., the system has a memory waiting longer makes the event more certain. Whereas the random events, their exponential distribution model events that occur at a constant average rate but at random intervals. That is, the probability of the next shock or arrival does not depend on how much time has passed since the last one. The application is for bulbs failed by random surges, not physical wear. Buses arriving in heavy traffic where they get clumped randomly rather than following a strict timetable. We experience the late arrivals of buses, trains because of the heavy traffic. It may be randomly occurred. Let us look at the statement of exponential distribution. After understanding the concept behind the memoryless property, if x is an exponential distribution, for every constant a greater than 0, probability of y less than or equal to x, given that x greater than or equal to a is equal to probability of x less than or equal to f here for all x where y is equal to x minus a. The interpretation is, given that the event has already lasted at least time a, the probability that the remaining time y is less than x is the same as the probability that a fresh start X is less than x. The proof of the theorem, proof of the memoryless property. The probability density function of an exponential distribution is given by f of x is equal to lambda e power minus lambda x for all x, positive x and positive lambda. Using the conditional probability definition, probability of a given b is equal to probability of a intersection b divided by probability of b. Here a is, let us assume that a is equal to probability of x less than or equal to y, and the event b is probability of x greater than or equal to a. Using the conditional probability, probability of y less than or equal to x, x greater than or equal to a is equal to probability of y less than or equal to x intersection of x greater than or equal to a, given that, divided by probability of x greater than or equal to a. Here, to understand this second step and third step, here the condition x minus a less than or equal to x, if we add a to both sides, this is equivalent to x less than or equal to a plus x, this term. If x greater than or equal to a, this means x must be at least a. The intersection logic is, when we use the intersection symbol, we are looking for the range of x where both the conditions are true simultaneously. That is, x must be greater than or equal to a, x must be less than or equal to a plus x. Combining these two boundaries, the range of x is restricted to the interval a comma a plus x. Therefore, we can write probability of capital X less than or equal to a plus x intersection x greater than or equal to a, that implies a less than or equal to x less than or equal to a plus x. So we can write this numerator as probability of a less than or equal to x less than or equal to a plus x divided by probability of x greater than or equal to a. Let us calculate probability of a less than or equal to x and less than or equal to a plus x. We know that for exponential distribution, f of x is lambda e power minus lambda x. Here the range of x is a to a plus x, integral a to a plus x lambda e power minus lambda x. Similar to our derivation of mean and exponential distribution, lambda comes out for e power minus lambda x. The integration is e power minus lambda x divided by minus lambda. Lambda gets cancelled. Minus 1 comes out. Substitute the maximum and minimum values. E power minus in place of x, a plus x minus e power minimum value lambda in place of x, a. By simplifying this, apply minus to this equation. Minus plus minus e power minus lambda a minus e power minus lambda a plus x. This is equal to, by commoning lambda a, e power minus lambda a into 1 minus e power minus lambda x. Now let us calculate the denominator probability of x greater than or equal to a. This is e power minus lambda a. We substitute the numerator and denominator. Probability of y less than or equal to x given x greater than or equal to a is equal to, this is the numerator here. So 1 minus e power minus lambda x into e power minus lambda a divided by e power minus lambda a. E power minus lambda a gets cancelled. 1 minus e power minus lambda x remains. Remember, the cumulative distribution of x given by probability of x less than or equal to x is 0 to x lambda e power minus lambda x dx is equal to 1 minus e power minus lambda x. Both these right hand side terms are equal, so the left hand side terms also must be equal. This gives us the result. Probability of y less than or equal to x given x greater than or equal to a is equal to probability of x less than or equal to x. Hence the proof. Let us look at some examples of exponential distribution. Find the exponential distribution with parameter lambda is equal to 1. Also find mean and variance. Substituting lambda is equal to 1 in f of x is equal to lambda e power minus lambda x. F of x is equal to e power minus lambda minus x. X range is 0 and infinity. The mean of exponential distribution is expectation of x is equal to 1 by lambda. Here lambda is equal to 1. We can get mean is equal to 1. For exponential distribution, variance of x is equal to 1 by lambda square. That is nothing but 1 by, instead of lambda we substitute 1. Variance is equal to 1. Next exercise, if f of x is equal to 1 by lambda e power minus lambda minus x by lambda, the range of x is 0 to infinity, lambda greater than 0, we find mean and variance. Look at the f of x value. Instead of lambda, we have 1 by lambda. So we can directly substitute, instead of the mean of 1 by lambda, instead of we can substitute lambda directly. This is the alternative parameterization where the rate is 1 by lambda. Here expectation of x is equal to, for lambda it is 1 by lambda, for 1 by lambda it is lambda, opposite. Variance is expectation of x square minus expectation of x whole square. This is equal to 2 lambda square minus lambda square. We can get 1 lambda square. So the mean is lambda and variance is lambda square. Thank you.